Alright guys, welcome back to Underground Science, and in this video we'll be talking about the Fick's law, especially relating to the alveoli of the lungs. Alright, so let's go and get started. So let's go ahead and first write down the Fick's law. Okay, so the Fick's law right here. Fick's law. Alright, so the Fick's law, let's go and write it down first, and we'll solve for something called flux. Alright, so first, let's go and write down our Fick's law. I'll explain the parts later, right? So we have this, and we have the surface area, and we have the change in the concentration of pressure, right, of one area to another, and then we have our diffusion constant, and we divide it all over thickness, all right? So one other thing to mention here is that the diffusion constant also has a formula to it that we can substitute for. All right, so let's go and write the equation again, but substitute a different equation for the diffusion constant, right, or diffusion rate or constant. So this is called the diffusion constant, or also the diffusion rate. All right, so the way you would solve diffusion constant is this. So let's go and write it down again. So this is going to be the cross-sectional area times the change in the concentration of pressure, right, or the difference, I should say, of one place to another. And we can substitute this equation in terms of solubility of whatever particles that we're talking about over, oops, that's not a good, sorry about that, that's not a good dividing sign, over the square root of the molecular weight. All right, over the square root of the molecular weight of those individual particles. And then we can go ahead and divide all of this by thickness. But what we're trying to actually solve for here first, before we start talking about Fick's law, is something called flux. All right, so right now we don't have flux. Flux is this symbol that you see here with the V and the dot. It pretty much represents the rate at which molecules will move across a certain membrane. All right, but what flux is going to be represented as is this. So the V with the dot over A, this whole value as a whole is going to be called flux. All right, and remember, A is the total surface area. All right, so it's the total surface area. So that means flux is going to be the rate at which those molecules move, right, down that specific membrane in that surface area. All right, so that means that we'll see later if our surface area is really small, right, even we can see with this equation, if our surface area is small, then we won't see much diffusion. And when we're talking about we won't see the rate of the molecules that are moving. The rate at which those molecules move across a certain membrane is going to decrease. All right, so this is flux. All right, that's what I was trying to get to. And so what we're going to do is let's just go and see how these components of the Fick's law. Let's see how these components play when we're talking about the lungs. All right, so let's go and quickly draw this out. Let's go and draw our arterial coming here, and make sure to go and check out the cardiovascular playlist if you're not familiar with the heart and a little bit of the lungs. We have our arterial here, then it joins in our capillary, right, and this is deoxygenated blood, then our venule, right, and then it gets a little bigger, and then it joins into our pulmonary veins, which then dump to the left atrium of the heart. Right, and then over here we have space for our huge alveolus that we're going to zoom into. So this is going to be one alveolus that we will zoom into. Kind of looks like an apple, but trying to represent an alveolus here. So this is an alveolus. One big alveolus. This is right here is our pulmonary capillary. Pulmonary capillary that, remember, initially started with our pulmonary arteries of the heart. Pulmonary capillary, which is deoxygenated, so I tried to represent that in blue. And then this is our pulmonary venule. All right, so pulmonary venule. which is now oxygenated because of oxygen diffusing from high to low concentration. Okay, so what happens here that we can look at in Fick's law is that, let's look at the surface area, right? The total area first. Initially we have this much area, right, in the alveolus. But what happens if we decrease the amount of area, right? If we decrease the amount of area based on this equation, remember this right here, this symbol represents the rate at which the molecules will move across a certain membrane. So this right here, this barrier from the separating the alveoli from the blood vessels, right? If we decrease the area, so make this whole alveolus smaller, we're going to decrease the rate at which the molecules, or for this, in this case, oxygen, can move to the blood vessels, right? The pulmonary blood vessels. So that's that. So that's the surface area. So what I mean by that is this. So if we drew it like this instead, right? If we drew it like this instead, right? Like if we see someone with alveolar collapse or with someone with emphysema, right? Where their elastin fibers aren't working properly, right? Because of all the elastases and other factors can play a role too, right? But if someone with emphysema or just alveolar collapse or a decreased amount of elastin, if their surface area is low, oxygen, because of Fick's law, remember this is, so let me go and write this down. So this is the rate, oh God, sorry. This is the rate at which, so let's go and write this down first. So this is the rate at which molecules will flow down, right, or diffuse down, will flow down a certain membrane, all right? Will flow down a, let's go and pick this up here, a specific membrane. Or you could think of it as a barrier, right? So that's what that symbol means, right? And remember, we say flux if we're talking about the rate at which those molecules flow, given a specific surface area, right? So if our surface area decreases, our whole rate at which the oxygen molecules can flow to the pulmonary blood vessels will also decrease. Similarly, right, if we increase the surface area of our alveoli, our flow rate, or our, I should say, our rate at which the molecules will flow into our pulmonary capillaries will increase. All right, and so let's go and look at this now, the difference in pressure. If we put a bunch of oxygen here, right, because we have such a high partial pressure of oxygen in our alveoli and a low partial pressure of oxygen in our pulmonary capillaries, right here, there's only like a few, let's say, because of that huge pressure difference right here, this is going to be such a positive value because P1 represent this, P2 will represent this. This has so many more oxygen molecules, such a high partial pressure of oxygen that because it's going to end up being a large value, it's in the numerator, which means the rate at which the oxygen molecules can flow down the certain membrane or barrier will increase. All right, so that's the difference in pressure. And so the same thing plays with solubility, right? If the molecules are, if you increase the solubility of those molecules, we're going to increase the rate at which the oxygen molecules, in this case, will flow down into the pulmonary blood vessels. And then again, guys, the molecular weight, right? Now the molecular weight, if you increase the molecular weight, what's going to happen is that the denominator of this separate fraction of the diffusion constant will get bigger, which means this whole value of the diffusion constant will get smaller. If this whole value gets smaller, the whole numerator gets smaller, which means that our whole rate at which the molecules will flow will also get smaller. So if you increase the molecular weight of each particular particle, it's going to take longer for it to really flow down into pulmonary blood vessels. And last but not least, in something like pneumonia or something where we have fluid buildup here, right? And also if it gets a lot, then we have fluid buildup in the alveoli too, which is what pneumonia is. Then the thickness increases. The thickness being all this fluid here, right? Because we'll go over this, and we'll go over the thickness in terms of the layers that are between the alveoli and the pulmonary blood vessels, right? Because we have surfactant production here, lining the alveoli, the inner part. Then we have the actual epithelial cells, the type 1, type 2 pneumocytes. Then we have a small layer of a basement membrane collagen type fibers on the outside of the alveoli. Then we have connective tissue, and then we have the tunica intima of the cat. Like, we have a lot of layers in order between the alveoli and the pulmonary blood vessels, which contributes to thickness. On top of that, if you increase the thickness by all this fluid overload, the denominator of Fick's law, right, of the Fick's law equation will increase, which means that the whole value at the rate at which the particles can move down a certain gradient or membrane or barrier will then decrease. All right, so it's going to be harder for these oxygen molecules to get down. And we see this in the pathophysiology of COVID-19, so go and check those videos out. All right, so that's pretty much what Fick's law is. All right, so you can compare it to real life by talking about the lungs, because as we saw, each and every component of this equation plays a role in how we talk about the thickness and the barrier and the molecules of the lungs, and how how the rate at which the particles can increase or decrease as it tries to flow down to the pulmonary blood vessels of the lungs, all right, that are near the alveoli. So that's it. That's Fick's law, right? Hopefully that this video was helpful and hopefully made sense to you guys. Make sure to tune into my future videos. We'll talk about more cool topics about biochem, physics, and chem. Don't forget to hit that notification bell, like, and subscribe. See you guys later, and stay safe.